Let's solve problem 4.11 from the textbook. The question gives us the utility function u of q1, q2 is q1 to the 0.75, q2 to the 0.25, and asks us what the optimal bundle would be if the price of good 1 is 1, price of good 2 is 2, and the consumer's income is 80. So let's set up the maximization problem first. So we want to maximize the consumer's utility subject to the budget constraint. So in other words, we want to choose Q1 and Q2 to maximize Q1 to the 0.75, Q2 to the 0.25, subject to the constraint that Q1 times P1, which is 1, plus Q2 times P2, which is 2, so 2Q2 equals Y, which is 80. So let's do this in a few different ways. I'll give you first the tangency condition. So what we're going to do is we're going to set the marginal rate of substitution equal to the negative of the price ratios. In other words, we're going to set the marginal rate of substitution equal to the marginal rate of transformation. If you go back, we saw that the marginal rate of substitution for Cobb-Douglas utility, so if the utility function is u of q1, q2 is q1 to the a, q2 to the 1 minus a, then the marginal rate of substitution is minus a divided by 1 minus a, q2 over q1. So this is something we had solved earlier, so we won't redo that. What we'll remember is that this is the marginal rate of substitution for a Cobb-Douglas utility function. Now what we've got here is a Cobb-Douglas utility function where a is 0.75. So plugging in a equals 0.75, we've got the marginal rate of substitution is minus 0.75 divided by 1 minus 0.75, which is 0.25, times Q2 over Q1. And that has to equal the marginal rate of transformation, which is minus P1 over P2. So remember, P1 is 1, P2 is 2. So we've got the negative signs cancel. So 1/4 and 3/4, so these cancel out to 3. So we've got 3 times Q2 over Q1 equals, remember this is 1 and this is a half. So we've got 3 times Q2 over Q1 equals a half. So if we multiply both sides by 2 and multiply both sides again by Q1, we get Q1 equals 6 times Q2. So we've got one equation with 2 unknowns. Let's go back to our budget constraint and plug this in so that we can then solve for Q2. Remember, the budget constraint tells us that Q1 plus 2Q2 is 80. So if we plug in Q1 here, we get 6Q2 plus 2Q2 equals 80. So 8Q2 equals 80. So Q2 has to equal 10. So if Q2 equals 10, then Q1, which is 6 times Q2, has to equal 60. So those are that's the optimal bundle. So Q1 star, Q2 star equals 60, 10. Okay, so that's the first way of solving this problem. Let's do another way. It's a little bit longer, but we'll do it another way. We're going to do the substitution method. What we're going to do is we're going to substitute in the budget constraint. Remember, Q1, if we solve for Q1, the budget constraint, remember, was Q1 plus 2Q2 equals 80. So if we solve for Q1, we get Q1 equals 80 minus 2Q2. So if we plug that into the utility function, we just get 80 minus 2q2 to the 0.75 times q2 to the 0.25. And so all we have to do is choose q2 that maximizes this. So let's write down our first order condition. We just take the derivative of this whole thing with respect to q2. So we can use the product rule and the chain rule. So using the product rule, we get the derivative of this thing with respect to q2 times q2 to the 0.25 plus the derivative of q2 to the 0.25 times this thing. Right? So that's what this part is. Okay, so let's first look at this term. We use the chain rule, and we've got a minus 2 in here, so we get minus 2 times the derivative of this with respect to q2, so we get 0.75 using the exponent rule times 80 minus 2q2 to the 0.75 minus 1, and this q2 to the 0.25 just comes down here as if it were a constant. Now we do the second term. We take the derivative of q2 to the 0.25, so we get 0.25 times q2 to the 0.25 minus 1, and this part shows up as if it were a constant. Okay, now it looks a little bit messy. It's still a little messy even though we've erased all the markings, so let's clean it up a little more. Now we've got this minus 2 times 0.75, so that's just minus 1.5. Keep the 0.25 here. Now, 0.75 minus 1 is minus 0.25. So if we take 80 minus 2q2 to the minus 0.25, that's 1 over 80 minus 2q2 to the 0.25 times q to the 0.25 plus, same thing here, we've got 80 minus 2q2 to the 0.75 divided by q2 to the 0.75. Just realize there's a missing 2 here. That has to equal to 0. So that's what we have here. Now we can move one of these to the other side, and so we have that this bit has to equal this bit. Now we've got here q2 divided by 80 minus 2q2 to the 0.25 equals 80 minus 2q2 divided by q2 to the 0.75. What we could do is multiply both sides by q2 divided by 80 minus 2q2 to the 0.75. q2 divided by 80 minus 2q2, 0.75. Notice on this side, they cancel out. However, on this side, we add up the exponents because we're multiplying the same thing. So we've got 1.5 times q2 divided by 80 minus 2q2 equals 0.25. Multiply both sides by 4 and cross multiply, and you end up with 6 times q2 equals 80 minus 2q2. In other words, 8q2 equals 80, so q2, the optimal q2 star is 10. Now we can go back to our budget equation. Remember, q1 is 80 minus 2q2, so 80 minus 2 times 10 is 60. So our optimal quantity Q1 is 60. So then, again, we found our optimal bundle. Fortunately, something would be terribly wrong if this weren't the case. We get the same answer doing it this way as we did using the tangency condition. Now the book gives you one more method, which is the Lagrangian method. I'm not going to do that, but you're welcome to use it if you're comfortable with it.